Okay, here we are in the lab again, and this is episode 1, the very first episode of a new video series. So what we're going to do is we're going to build a hard disk emulator. So that means we're going to take an SD card and we're going to retrofit it into this retro computer from 1993. And this is the retro computer that we built in the Retro PC video series. So it's having hard disk problems. The disk is getting ready to fail. I don't have enough space to do what I want, which was always a problem in the old days. Never enough space, never enough memory. But so we're going to build an IDE drive emulator so that we can use a modern SD card and stick it right in here and use it as a hard disk. So that entails quite a few things we have to do, but it's not terribly complicated, but there are aspects of it that gets complicated. All right. So the very first thing we have to think about is how this SD card is going to interface into this computer. So in those days, the 386, the 286 on up used what they call AT bus. It's a 16-bit interface from the motherboard that you can plug a card into. You can plug in like a hard drive controller, a serial card, sound card, Ethernet card, anything, all kinds of options, but you just plug it in on the motherboard and the motherboard communicates with it through the ISA bus. So let's take a look at what the ISA bus looks like, and then we'll get into more detail with it. Okay, let's zoom in on the computer and look down here at the motherboard. And this is the ISA connectors, the physical bus interface that we will be talking about. Okay, so that was the physical ISA connector on the motherboard. All right, so then you need a card that plugs in there. So it's too early to like order a PCB to plug in there because we don't know anything yet. So we're going to start out with a prototype. We have to build a prototype first. And so we're going to use this thing right here. This is an AT bus prototype card. And I'll leave a link up here where you can get it. And so we're going to build our circuit on this. And so that's pretty much the physical part of it. And so in order to build the card, we have to build a schematic. And in order to build the schematic, we have to learn more about the ISA interface so that we know what signals we need to use and how we need to use them. And that can get a little bit in depth so that's going to be the interface part. So there's going to be three parts to the prototype, and it's going to be the interface that interface and handles the signals of the ISA bus. Then it's going to send it to the microcontroller, and then the microcontroller is going to talk to the SD card. All right, so that's the 3 sections. So we got 3 sections: SD card, microcontroller, and ISA interface. So we will start next with the ISA interface and see what all happens on that. Okay, so here's the pinout for the ISA interface. And as you can see, there's quite a number of signals, but we're only going to worry about the signals that we're going to use in our application. D0 through D7 is the lower 8 bits of the data bus, and it is bidirectional. It goes both directions. You can read and write. Okay, and then next is the address bus, A0 through A19. and it is unidirectional, and it is coming out to our I/O card. There are also 4 grounds that provide a return path for all the signals in the system, and we will be attaching to all 4 for maximum noise immunity. The ISA bus also provides power. We have 5 volts plus and minus, and we have 12 volts plus and minus. And we will be using the plus 5 volts to power our I/O card. And there is also a reset signal that provides a way for the CPU to reset the system hardware. So we will use that to reset our microcontroller whenever a reset on the front of the computer is pressed. Next is the I/O read and the I/O write lines, which indicate a read or a write to the I/O hardware, which is not the same as reading and writing from memory. The AEN signal, which stands for address enable, is used to distinguish between a normal I/O cycle and a DMA cycle, which is a direct memory access, which we probably won't do. At least we won't be doing it in the beginning. So DMA is when an outside device like an I/O card wants to directly access the memory without going through the computer CPU. And that speeds up access times. SD8 through SD15 is the upper 8 bits of the data bus. SD stands for system data. I don't know why they distinguish it that way, but it's the upper 8 bits of our 16-bit data. And last but not least, we have the IOCS16 signal, which stands for IO chip select 16. So the I/O cards pull this low to indicate to the CPU that they can send and receive 16-bit wide data. And I'm including this as an option because I don't think we have to have it, but I want that option available if we should wish to use it. So that's essentially ISA bus. So it's kind of like standard textbook microcontroller or microprocessor interfacing from the old days. So if you get a book on the 8080 or the 8086 interfacing, 8085, any of those old processors, it will help you learn more about interfacing. That's where I learned how to interface, was from those kinds of books back in the day. So the next thing we want to do is we have to discuss how the memory addresses, how the addresses, it's I/O, not memory. So how the I/O addresses get decoded. Because like I was saying, there's a certain address range that the hard drive is expected to respond to. So there's 8 registers and a control register at a different memory or different I/O space. So we have to decode for those, and we'll do a quick rundown of how you decode addresses, and then we'll discuss how we are going to do it. Okay? Okay, so normally with ISA, for your base address, you just decode A8 through A15. So that makes it a little easier. And so that gives us a base address possibility here. And we're going to shoot for the base address of 100, all right, for this example. And so that means that we need an output of a low output, a chip select output for our logic, and it's got to be active low because that's the standard normal thing. And so if you look at this binary representation of the addresses, so this is 0 through 7 here. So we can X that out so that we don't get distracted by it. We don't care in this circuit, we don't care what the lower 8 bits are. We just want to decode for this. So when all the address bits are 0 except for A8 and it's a 1, then we want this to be low, and only when that happens, okay? So that means we have to invert all the zeros to a 1 and run it into an AND gate, all right? So let's get some inverters here. Okay, so now we got our inverters. Let's get an AND gate. Okay, so now let's connect the first 2 lines like that. And so the logic is that when the A8 is a 1, which we want, and A9 is a 0, then these are both 1s here. So with an AND gate, that makes an output of a 1, which is not what we want here. So we will have to invert the output, but we have to get all these inputs in our circuit first, and then we will invert it if we need to. So that's what we end up with if we use 2 input AND gates, but you can use an 8 input AND gate if you wish. So let's get our lines hooked up and check out our logic. Okay, so that's how we hook it up. So now, when all of these over here are 1, which they will be if that address here goes in here, these will all be 1s. This will be a 1 on the output. So we need a low. So we just need to invert this, and we will have our logic circuit. And just like that. So as you can see, when this address here gets put on these, the inputs, then the output here will go low. And that's what we want. This will turn on your device when that address is put on the inputs. Okay? So that's the idea behind address decoding. But this can get simplified quite a bit. So since this is an AND gate that is inverted, then we could use a NAND gate to replace this. So we could do this like that, and then we will eliminate the need to invert this because the NAND will invert it for us. Okay, and it can be simplified more, but this is the basic idea behind the address decoding. Okay, so this is the decoding for base address 0100, but what if you have a couple different base addresses that you have to access in the same I/O card? So this just happens to be the way the ATA specification is, that 170 to 17F is the registers for the primary ATA, but it has a control register at 3F6, which gives us a base address of 300 and with the upper 8 bits. So that adds a little bit of complexity. So what do? So we have to decode for that one as well. And in order to decode for the second base address, we have to do a complete decode of all 8 inputs in order for it to function properly. So then at the end of each decode, we OR them together. And since it's got to be inverted for a low, active low, then we use a NOR gate. All right. So anytime we get this base address on here or this base address on here, then we get a low on the output here. All right. So then you can see there's a lot of logic here to put on a board. You can get an 8 input AND gate in the chip. So that would eliminate this. There'd be one chip here, one chip here, but then you still have a NOR gate here. And usually the smallest you can get is a quad of four 2 input NOR gates in a chip. And then you got 7 hex inverters, and usually you get 6 in one package. So then you have to have 2 packages. And so you got 1, 2, 3, 4, 5 chips just to do this decode. But there is an easier way. Okay, so you've seen how we decode an IO address. So but there was a lot of chips. We had a lot of chips. It takes a lot of chips to decode that. And you can simplify it. There's a lot of like techniques you can use. There's Karnow maps and different things. But that's kind of complicated and out of the scope of what we need to worry about anyway, because there's a simpler way to combine it all into one single chip. And that's programmable logic. And that's what we're going to do, because it is so much easier and you can rewrite the logic. It's like flash memory. You program it to decode what you want and you're like, oh, I want to add this signal, or oh, I messed up or something. Well, you can just reprogram it. And you just only thing is you have to have it in a socket on the board so you can take it out and put it in the chip programmer. And you have to have a chip programmer, but you can get one on Amazon for like 80 bucks. And it's a really good thing to have. So I'll put a link up there on the one I got. It works really good. I haven't had any trouble with it. I haven't used it a lot, but I haven't had any trouble with it. And it really simplifies stuff. So let's take a look at what a programmable logic chip is, and the one that we're going to use, and how it decodes. Okay, so here's the basic idea of a programmable logic device. Yeah, there's a PAL, which is like the original, and then the GAL, and the GAL is an enhanced version that allows you to reprogram the logic, which we will be using. But the basic idea is you have a couple of inputs here, and it goes through here, and here's an AND gate, and they're ORed together just like we have in our decoding scheme. And so you have these pull-ups here, and you have some fuses. And so the idea is, if you want it to be a non-inverting input, then you would blow this fuse, electrically open this up to where it's not, you can't, it's an open path here. So that eliminates this. And so you get this one to go through, and then this is pulled up by the 5 volts. So it's a 1. And so that your logic goes through and is ORed with this one. So you could blow all these fuses if you didn't need this input, and it'd be all pulled up, so that'd always be a 1. So you'd always get a 1 out here if this was a 1. And so that's the basic idea. So when you program it, you're just like either skipping over, leaving the fuse as is, or you're breaking it open electrically. And so that programs your logic. And they get a little more complicated too. They have flip-flops inside and stuff like this, but you just define your program in a text file, compile it, and then the programmer takes that file and programs these fuses based on the file. And that's the basic idea of how programmable logic works. So probably the next step is we're going to have to take a look at the software, the compiler that generates the program that you put in the chip. So that's called, the language that you use is called CUPL. Atmel has their own compiler for free, which is good, called WinCUPL. So we'll go check that out. I'll show you where to download it, and we'll check it out and write a little program. It's really easy to do simple stuff, but it gets really in depth. So I'll put a link up, but in my public directory in my domain antimatter.me, there is all the data sheets and the programming reference and everything for this whole video series, and other video series too. But this whole video series will have a directory for it up in there, and I'll send a link. All right, so let's check out CUPL and see what it has, what knowledge it has for us. Okay, so let's go to the download link first. And it's at Microchip's website, development tool /WinCUPL. I'll put the link up there and in the description. And so this is where you download it right here. It has some other stuff and an overview and all that stuff. And so that's where you get it. I already got it installed, so we don't have to go over that. And so let's take a look at it here. And so it's kind of primitive looking. Maybe version 2 looks a little better, more modern. I think this is pretty old, but it works. So the first thing you want to do is new and design file. And then you got stuff in here you can put in. All right. And we'll just hit OK. It asks you how many inputs. It's kind of like a wizard to help you out. So we'll just have 2 inputs. We'll have 1 output and no pin nodes. Pin nodes are for a future, more advanced thing. All right. So you'll probably want to rename it. So save as, and you can just call it like my device or whatever, PLD. That's the PLD file. All right, and just save it like that. And you want to save theirs? No. All right, so then you have your file here and everything. So you have to tell it what device if you want to generate an output file. So devices, and most of these here use mnemonics. This is your actual device name here. It says related mnemonics. I don't know why. I guess that's for the pal, and the G is for the gal. Remember, the gal is the reprogrammable one, which isn't applicable in this little demonstration right here. So you just copy this. For some reason, it does not put it in here for you. I don't know why. So you just paste it, and then you got to save it. Okay, so we got our file started. So then the pin, we're going to use pin 1 and pin 2, and then our output will be like pin 14. It does have to match the device. So you would normally look at the data sheet and see what pins you want to use and all that. But we're just doing a demonstration. So pin 1 is it's just like naming a variable in another programming language like C. You just name it whatever you want. And then we'll do it like we're doing address lines or something. All right, and then you can put your comments in here. All right, and then pin 14, we're going to call it like chip enable, but it's going to be active low, so you just kind of like, it's common practice to use _n, but it's your name. You name it whatever you want. And so then you have to do the equation. So you go like CE_n equals. So it's going to be active low. So that's like a not symbol if you're a C programmer. So then you put your equation in parentheses. So we'll go like AO ANDed. You could do OR, which is a plus sign, with A1 and into parentheses, and that's our equation. And that's our whole program right there. So we just save it. And it's pretty simple. You can get complicated. You can do a lot of crazy stuff, but this is basically how you do it. And so you hit run and device dependent compile. And it looks like it liked it. Compilation successful. And hit OK. And now it generates the files for you. All right. So then you're done. You created your file. All right. So you can just close that out or whatever. So the .jed is the JDEC file, and that's what you will load into your device programmer when you want to program your device. Okay, so that's how we use the CUPL language to describe how we want our chip to decode our address lines. And in our case, address lines, it could be any kind of lines doing any kind of thing. But just as an example, is our address lines. And so then we compile it and we create a .jed file, which is a JDEC file. And then we'll take that JDEC file and we'll load it into our programmer and we will program it into our chip. And then we can put our chip on the board and do some experiments. Okay, so let's jump over and take a look at the programmer. Okay, let's take a look at the programmer and where you can get it. So if we come over here like this, at Amazon, this is the programmer that I got, the T48, and it's a TL866-3. 3 means third generation, so it's a newer thing, so it does a lot more devices than the older ones. So you might want to take that into consideration. And this is like the no frills, no options one, where because all I needed was the programmer, and then we got our little adapter boards that we can just stick in there. So I didn't need any adapters or anything. But you can get these ones in various, you can get all of these like sockets and stuff, which might be handy for you. And or you can go down a step. This is a little pricey. This is a little less pricey, but this is the bare programmer, and that's what I got. So that's where you can get it and how much it is, and you can find it in other places, and you should search and look and decide for yourself. So then this is where you download it here. Download the software for it, because the software they just give you a link and that's it. So this is the link to download the software, and it's kind of weird. I didn't know what this meant at first, but this is just like the servers where you can download it. It's the same file, except when you go see, this is the one that we have here. That's the manual. This is let's see, right here's the software. 12.97 is the one. So these are just the places that you can download at the server. So if you go to the overseas one, then you can get this right here. The 1297. This is what we want. We don't have the T76, so we want this one here. And so then you download right here, and there you go. Okay, so that's what you have to do. You have to get the programmer, and then you have to download the software. All right, so it's not too bad. So let's take a look at the software. So this is basically what we got. And so if your program is plugged in, then it will find it and it'll load everything. All right. So then you want to load up your device that you're going to program. So in our case, we'll use this one. And so then all you have to do is to open your file, and that's our little JDEC file here. And so it loads it in here. You can see it changed like a bunch of stuff. And this is our what we're going to program on the chip. So then you just load your chip into your programmer, and then you just have device. You can read it, verify it, program it, or anything like that. Okay. So that's pretty much it. Okay, so now we know how to decode address lines. And then we learned how that decoding multiple base addresses create more complexity, and how you would require a lot of like discrete logic chips. So, and we want to get away from that because we don't, first of all, we don't want to take up that much space. We don't want to add that much complexity. And so we are moving towards programmable logic. So we learned how to create a simple CUPL language file and compile it into a JDEC file, and then load that JDEC file into our programmer and program our chip, and where to get the programmer and how much it costs and what programmer to get and all that stuff. So we know all this. So the next step is to move on to defining our interface with the ISA bus in more detail so that we can actually create the real program for our programmable logic chip. And then we can get that thing on the board and we can see if it works. So that's kind of the next step. And that's in the next video. So that concludes this video for right now. And I will see you in the next video.